Good afternoon, everyone. We will start our discussions on week 5. I welcome you all to the Power System Engineering course of NPTEL by Professor Debapriya Das. For this week, we will first see the brief concepts that need to be used for this week's question and answer assignments. After this, we'll solve the previous year assignment and followed by doubt clearing. So for this week, the questions are based mainly for corona calculations. So we'll see the brief overview of corona first. So basically, so this phenomena of corona is usually observed for transmission lines above the voltage level of 220 kV. So those lines, those who are operating at a voltage level of 220 kV or greater. So for those lines, this phenomena of corona is evident. So due to this, what happens is it leads to power losses, additional power losses in the line due to this corona. Secondly, it also leads to interference with the neighboring communication line. So electromagnetic interference with the neighboring power cables. So basically what happens is whenever you have a transmission line, along with that your power line or communication line is also there. And due to this phenomena of corona, what happens is there is electromagnetic interference between both these two lines. So what will happen that the communication line, that signals that are passing through that communication line, they are distorted due to this corona phenomena in the power lines. And it also leads to noise, a certain hissing sound that we call, that is that you can hear whenever there is formation of this corona. And also it may lead to formation of ozone gas basically. And this ozone gas you can identify by its smell or odor. And due to this phenomena of corona, we need to design our conductors and our towers, at what height you need to basically suspend the conductors, and designing of the conductors, like what diameter of the conductor you need to keep, what spacing between the conductors should be there, and design of the insulators. So these should be taken care of, or these uh, designs should consider corona as a factor. Additionally, we also require maintenance of these lines before basically this before rainy season or humid weather. So corona is more evident during when the air is full of moisture. So basically during this rainy season or humid weather condition, so the lines or conductors maintenance need to be done, conductor insulators. So the yearly maintenance is carried out normally before this season so as to avoid the corona, which may lead to flashover also. So as to avoid corona. So what is this corona and how it takes place? Let us discuss that next. So what happens is whenever you have a conductor or uh, so whenever you apply some voltage across this, So whenever a voltage is applied to the conductor, so that will lead to the formation of your electric field between them, right? And what it will lead that uh, the air between the conductors, it basically consists of different ions also. So air between the conductors is consisting of ions. So in normal condition they will be neutral ions. So whenever there is this electric field will be there, though ions will attain velocity and they will strike the air molecules. So what will happen is, let's say this is a neutral molecule. So whenever high velocity or high speed ions they will strike this neutral molecule, it may lead to formation like this neutral molecule will be separated into a positive ion and a negative electron, as we say. So this breakdown will happen, and again these ions, what they will do, they will strike other neutral air molecules. So whenever again cascaded type of phenomena will basically happen, so they will strike other air molecules, so new ions will be formed, and so and then again cascading, these new ions will strike other molecules, and similarly the number of ions or charged particle will increase rapidly in a cascaded fashion. So whenever the number of ions is increased, so what will happen is at certain point the saturation will take place, and what will happen is now the air starts conducting. So air will no longer be your dielectric, it will be it air will become conducting. Then what will happen? There may be a breakdown and there will be arc formation between the two conductors. So in the lab also, laboratory setup, this arc formation or this, what we say, this disruptive voltage, also it is usually you test it in the high voltage laboratory experiments, where let's say, so in that experiment what you do, so experiment, so you take two conductors, so let's say first case they may be spherical conductors, or you may test it for a spherical and a pin type. So this will be pointed like this, or a pin to pin. So in this experiment, for different types or combination of conductors, what you do, uh, and let's say this distance is d between the conductors. So first you fix the conductors at a fixed distance d. Then you gradually increase the voltage applied to these conductors, and you observe that at certain V the air will start to conduct at certain V, and the air will start to conductor and a flashover takes place. So how you can determine that flashover has taken place is at that time a spark will take place. Basically, you will see a light formation and glow will be there. So then you can deduct that the flashover has taken place, and the voltage corresponding to which the flashover has taken place, that is called the critical disruptive voltage. So this is the minimum voltage at which the air is becoming conducting and a flashover occurs. So this was first part. This was one, and in the next you increase or decrease this distance, and you observe at the critical disruptive voltage, basically V C. So whether it is increasing or decreasing with the change in distance. Now what happens when there is a spherical conductor and a pointed conductor? Basically for a sphere, what happens is there is uniform distribution of charge on this its surface, right? But here in on the surface of this pin, these more ions are accumulated at this pin side. So what happens here is for the same distance d, here also same distance d, in the experimentally what we observe that the V disrupt critical or the critical disruptive voltage that will decrease. So flashover will occur at a voltage, let's say this was VC1, VC2, VC3. So that voltage VC2, and that is less than VC1. So flashover will be quicker due to this pointed or pin type conductor, right? Because earlier the electrons were here freely or uniformly distributed over this spherical conductor, but here the ions are more concentrated at this pointed edge. So that will lead to flashover voltage at a lower voltage. Similarly, for VC3, when we have two pin type conductors here, where charges are accumulated at this pin for the same distance d between the same distance d between the conductors, the flashover voltage VC3 will happen even more earlier or at a lower voltage than VC2. And this was VC1. So this type of experiment, one experiment is done in the high voltage laboratories. Now let us see that whenever this basically what are the characteristics of this corona formation. So, firstly, there is a luminous glow of violet color. Then, secondly, you may hear a hissing sound, and then you may observe a peculiar odor of gas formation, odor of gas, which is basically ozone gas. So when you basically see this violet light, hear this hissing sound, or have the smell of this ozone gas, you can say that the corona has taken place. So these are the characteristics of corona. And this corona basically depends upon the ratio of conductor diameter to the spacing between the conductor. So let's say the conductor diameter is D, and the spacing between the conductor is capital D. So this radius will be D by 2. So if this ratio between spacing between the conductor and the radius of the conductor, so if it is greater than 15 or 18, I can't remember exactly. So during that condition, corona will take place. Sorry, when it is less than. So whenever this ratio is less than 15, so then there is chances of corona formation. Or this is the chances of flashover actually, not corona. And for your regular overhead transmission lines, this ratio is always greater than 15. So for a transmission line, flashover is nearly impossible, we can say. Now, let us see that, let's say we have two conductors. So let's say one is carrying positive charge plus Q, another is negative charge minus Q. And let's say at certain distance X at point P, and D with the distance between these conductors. So what we need to find is let's say the electric potential E at distance x from the plus Q conductor. So this electric field, we can write it as Q by 2 pi epsilon naught x due to this conductor plus Q, and for the minus Q we will have minus Q by 2 pi epsilon naught, and this distance will be d minus x, right? So hence the electric field will come out as 1 by x plus 1 by d minus x. So we know at x equal to r there will be maximum electric field, and that E max we can calculate as putting x as r. So we get as q by 2 pi epsilon naught. I have denoted as small r, so let me write small r. 1 by r plus 1 by d minus r. So it will be same as q by 2 pi epsilon naught r into d minus r by d minus r plus r, so capital D. So let us assume that the distance between the conductor is much greater than the radius. So this will be nearly about D. So this D and this D will cancel out. हेलो, वो 5 बजे के बाद आ सकता है, मैं क्लास के बीच में हूँ अभी. Yes, so this will cancel out and we will get as 2 pi epsilon naught r. So that is the maximum electric field. And for the RMS, so this will be just E max by root 2. Now once we know this, now we can integrate it to find the potential, right? So this potential between these conductors, basically if I name them as A and B, VAB will be integration this d minus r to r ex dx, right? Or r to d minus r ex dx. So we had seen that ex was basically q by 2 pi epsilon naught 1 by x plus 1 by d minus x. So this will be 1 by x integration is ln x. Ln x minus, because here x has coefficient of minus, so ln d minus x d minus r to r. Then let us substitute. So this will be ln d minus r minus ln d minus d plus r minus ln r plus minus minus will become plus ln d minus r. So we get it as q by 2 pi epsilon naught 2 ln d minus r minus, this is basically ln r, right? 2 ln r. Now you know ln a minus b is ln a by b, q by 2 pi epsilon naught 2 ln d minus r by r. So 2 will cancel out. So q by pi epsilon naught ln d minus r by r. So that is the potential between the conductors A and B. And if I calculate the potential for one phase to neutral, that will be VAB by 2. So it will be Q by 2 pi epsilon naught ln of, basically this D minus R, we had seen that it can be written as D, where we consider this D is greater than R. So D minus R is nearly equal to D. So ln D by R, this is in volts. So from previous one, so V phase to neutral, we saw that it was Q by 2 pi epsilon naught ln D by R. So from here, V phase to neutral by R divided by R in both sides. So 2 pi epsilon naught R ln D by R. So from here we get Q by 2 pi epsilon naught R as V phase to neutral R ln D by R. And already we had seen that this Emax, so it was because Q by 2 pi epsilon naught R, we had seen that was Emax here, right? Emax. And we found out that Q by 2 pi epsilon naught R, which was Emax, is same as V phase to neutral divided by R ln D by R, where D is spacing between these two conductors and R is the radius. So next, let us see the critical disruptive voltage. So what is this? So critical disruptive voltage, it is the minimum voltage at which complete disruption of air, at which complete disruption of air takes place, at which complete disruption of air takes place. So in general, the breakdown strength of air so the breakdown strength of air at a pressure of 760 mm and temperature of 25 degrees Celsius. So this is known as STP, standard temperature and pressure. So that is 30 kV per cm, and this is max. So for RMS for air at STP, that will be Emax by root 2. So that will come out as 21.21 kV per cm. Now for finding out this disruptive voltage at a temperature or pressure other than your STP, then we use a correction factor. So basically delta, so delta, that is known as your air density correction factor. So this delta is calculated as 3.92 times B divided by 273 plus T. So where B is your barometric pressure of Hg and its unit is in centimeter. So earlier, if you remember, it was 760 mm for STP, right? And temperature was 25 degrees centigrade. So this is 76 cm basically. And T is your temperature at the temperature at which you need to calculate or you want to calculate this disruptive voltage, and that is in degree centigrade. So for calculation of this V, this is your disruptive voltage basically, critical disruptive voltage at conditions which are not STP, at conditions not STP, you need to multiply your this air density correction factor to your earlier formula. So this is in kV. So let me write it clearly. So your V dash is R. E naught is at your STP, right? Delta D is spacing and R is radius, and this is in kV. Now let's say this is for your smooth conductors, right? So this is for smooth conductors where there is uniform distribution of charge. So let's say if there is due to decomposition of dust or there are which may lead to dust or other particles, smooth, right? Solid and smooth conductors. So this may lead to irregularities on the surface of the conductors, irregularities of the surface, irregularities or roughness on the surface. And if you have stranded conductors, right? So this stranded conductors. So what will happen is here the breakdown voltage V will decrease for all such for such situations your critical disruptive voltage decreases. So to account for this irregularities, we introduce a factor that is denoted as this M naught. So for polished ones, we take this M naught as equal to 1. For rough conductors, so between point M naught is between 0.98 to zero point 0.8 or 9 we can say. So again we can say disruptive voltage considering your atmospheric condition and conductor surface so that can be calculated as R G naught delta M naught ln d by R kV, right? So whenever this V dash it is applied to the conductor, so we can say that corona phenomena has started. But due to this V dash, this may not be visible. So what happens is for this at V dash the corona will start, but for visible corona we need further ionization. Further ionization is required. So for a radial field, So to reach a gradient of GV, we say at the surface of the conductor, to have a G naught at a distance, at a finite distance away from the surface, so when you applied basically this GV, then only visible corona will take place. So because when you apply V dash on this conductor, so here the G naught is there, but we know when this is the radial distance basically. So at a distance x, it will be G is less than G naught, right? So but for corona, what we need that here it should be G naught. Then only visible corona will happen. So to have a G naught here, we have to increase the potential here to some GV we are saying. So that when there here on the surface it is surface of the conductor it is GV, then at a certain distance x, we say this x, the it will be G naught, so that your corona can takes place. So this is known as your energy distance. And according to Peak, he calculated that this distance is equal to r plus 0.301 times of root r for two parallel conductors. So then your GV becomes G naught delta times this kV per cm. So if VV is denoted by the critical visual disruptive voltage as your critical visual disruptive voltage, then this is equal to GV times R ln d by R, or from here GV is VV times R by ln d by R, which is from here G naught delta 1 plus 0.3 R delta. So from here we can finally say this will be R G naught delta 1 plus 0.3 divided by R delta ln d by R. Basically this one is coming to this side. So again similarly if you take the irregularity factor and other thing, so then VV will become this R in place of G naught. You can put this RMS value 21.1, right, which we calculated previously for 30 was maximum, so RMS is 21.1, and M is for the irregularity, delta is for your atmospheric condition other than STP, R delta ln d by R, so kV, and this is your RMS. Now next we will see corona loss. So the ions, to keep moving or to remain in motion, they draw certain amount of energy from the supply. Draw certain energy from the supply. So this leads to the additional corona power losses. So again, from the peaks formula, they calculated this corona losses as 241 times 10 to the power minus 5 F plus 25 divided by delta square root of R d by d multiplied with Vp minus V naught square. So this is loss, so it will come in kilowatt, right? So kilowatt per kilometer per phase. So here F is the frequency, R is this radius, D is distance between them, and Vp is the operating voltage, and V naught is the critical disruptive voltage. So this is in your fair weather condition. So if you consider foul weather condition, so then your disruptive voltage will decrease, and we take it as 0.8 times the normal critical disruptive voltage. This is your fair. Now let us see the factors affecting this corona losses. So firstly is frequency. So I'll write the formula for loss here. So it was some 241 into 10 to the power minus 5 F plus 25 by delta R by D into Vp minus V naught square. So firstly that is frequency F. So here you can see that whenever F will increase, your P will also increase, losses will increase, right? Because they are directly proportional. So as F increases, P loss increases. So what it will mean that for DC, that is when F is 0, your PDC, they will be less than your PAC. So corona losses in AC is greater than DC. Nextly, coming to distance between the conductor, we can say, or the arrangement of the conductor. So let's say we have conductors arranged in this horizontal fashion. So what will happen to this middle conductor? So for this middle conductor, the electric field is large, right? Because it is in the middle of these two conductors. So what will happen? If the field is large, so this V naught or V critical disruptive voltage, that will be less. So if V naught is less, so here V naught will be less. So what will happen? This square term, then it will be more. Overall, this square term, it will be more. So your power loss will also increase. V naught is more, so Vp minus V naught is more. So its square is even more. So loss will also increase. So for middle conductor, the loss will be greater than the other two conductors. Similarly, the height of the conductors from the ground. So if it increases, the loss is decreases. Next, coming to the uh, this air density correction factor. That is your delta. So you can see it is in the denominator, right? So whenever delta will be decreasing, your loss will be increasing. So as delta decreases, your loss decreases. And you know delta, it was directly proportional to pressure by temperature. So whenever your pressure decreases or temperature increases, your delta will be decreasing, and that will lead to increase in losses. Next, coming to dust. So due to this presence of dust, what will happen? Your irregularities or roughness of the conductor, that will increase. So what will happen? Your critical disruptive voltage, it will decrease, right? We had seen. So what will happen if Vc decreases? So we have seen whenever Vc decreases, this term, it will increase. So your P loss will also increase. Now for this radius of conductor, next one is interesting. So here if you see in the formula, there are two terms. First is, from first one you can see P loss is directly proportional to R by D. So what it means, whenever the radius of the conductor will increase, your losses will also increase. Yeah, so whenever radius of the conductor will, so P was directly proportional to R by D. So whenever R increases, your loss also increases. And also this P, it is directly proportional to Vp minus V naught square. But we know this critical disruptive voltage is directly proportional to R, right? This V naught is directly proportional to R. Here we have seen VV, so it is R here. So whenever R will increase, your V naught will also increase. And we have seen here whenever V naught increases, Vp minus V naught will decrease. So square will decrease furthermore. So P loss will decrease. So on one hand, here it is increasing, but here you can see it is decreasing. But since this is having square term here, its effect is more. Decreasing effect is more. Decreasing effect is more than increasing effect. So overall, in general, we can say whenever radius of the conductor increases, your losses will decrease. Next, even there is bundling of conductors. So by using this bundled conductors, we know that the effective radius will increase. So again, R increases, we saw just now. V naught will also increase and loss will decrease. Next is another thing is whenever the conductor it is carrying certain current due to load, right? I load. So this load current will lead to some loss in the conductor I square R, which may lead to heating effect of the conductor. So this heating effect of conductor is a blessing in disguise, we can say, because whenever there is heating effect, we know that the temperature will increase. So whenever there will be temperature will increase, so if we have humid condition of air, so due to this humid condition, what will happen? There may be dew or frost formation over the conductor, right? Over the conductor, and due to this heating effect, due to the load current heating effect, so this will melt away the dew. Similarly, after rain, there will be water droplets over the conductor, and due to the heating effect, the conductor will dry out faster. So this will protect the conductor for the corona formation in the dew, in the humid air condition or after the rain. So for reducing this corona losses, we usually use hollow conductors or conductors with larger diameters or bundle conductors. And this loss formula, what we saw was basically Peake's formula, right? So this Peake's formula, it is more accurate whenever the ratio between this Vp and V naught it is greater than 1.8. So peak is more accurate. And whenever Vp by V naught is less than 1.8, we use your Peterson's formula. Peterson's formula is more accurate. So what is this Peterson's formula? It is 2.1 F Vp by log 10 d by r square into 10 to the power minus 5 into F. So this F we'll see corona. This is the corona loss function basically. Now this corona loss function F. So there is a chart for it given. So this varies with ratio Vp by V naught. So here you see in Peterson's formula, V naught is not there in the formula, but it is indirectly included in this F. So for different Vp by V naught, you will get you will take different values of F. And that is already given in a chart to you. So you need just to read it and use accordingly. So this using these formulas and this background, let us solve the assignment questions. So the first question here, the effect of corona can be reduced by number one, reducing the conductor size. Two, reducing the spacing between the conductors. Three, increasing the conductor size. Four, increasing the spacing between the conductor. So this we have seen basically to decrease this corona what we do, we use conductors of larger diameters or by the fact we use the bundle conductors for same only to increase the conductor size, and secondly by increasing the spacing between the conductor. So increasing both, so it will help in reducing the corona. Now next question. In humid weather, the corona occurs at a voltage A much higher than that needed in fair weather, B much less than that needed in fair weather, C equal to the needed in fair weather, D none of this. So this also we have discussed that whenever there is more humidity means there are more molecules present in the air, it is containing more number of ions, so it will increase the chances of corona. So that means your critical disruptive voltage, it is going to decrease. So corona chances will increase in humid weather. So corona may and the corona may take place at a less critical disruptive voltage. So it is B, much less. Next question. The effect of dirt on the surface of a conductor is to dash its regularity and thereby dash the breakdown voltage. So, whenever there is dirt on the surface, it will increase the irregularity because at certain points the dust will accumulate. So, there will be roughness or irregularity at those points, and thereby it will increase the breakdown voltage. Sorry, it will decrease the breakdown voltage because at these points there are greater chances of corona at lower voltage. So, next question, the breakdown strength of air at STP is 3 kV peak per mm. Then the breakdown strength of air in kV RMS per cm at 27 degree and 75 cm of pressure is. So we know that at STP it is 3 kV peak per mm, which is same as 30 kV peak per cm or 30 by root 2, which is same as 21.21 kV RMS per cm. So the air density correction factor we had seen delta was 3.92 B, where B is the barometric pressure, and 273 plus T. So this has to be in cm, this has to be in degree centigrade. So 3.92 B is given here as 75 and 273 plus 27. 10 carry on 10, 300. 3.92 into 75 divided by 300. So 25 is 3. This will be 25, 12 or 4. So 0, 9, 36, 3, 8. So this correction factor is coming out to be 0.98. So your V dash will be delta times V naught at STP. So 0.98 into 21.21. That will come out as 0.98 into 21.21 as 20.785 kV RMS per cm. Now next question number 5. An equilaterally spaced an equilaterally spaced three-phase AC transmission line has a total corona loss of 35 kilowatt at 220 kV, 45 hertz. If the supply frequency is changed to 55 hertz, keeping all other parameters unchanged, keeping all other the total corona loss as per Peake's formula will be so we know according to Peake the formula was if you remember it was some 20 roughly 3 times L into 244 by delta F plus 25 R by D Vp minus V naught square into 10 to the power minus 5 kilowatt. So here this 3 is for this because it is a three-phase line, right? So from here you can see P is directly proportional to your F plus 25. So basically PC1 by PC2 equal to F1 plus 25 divided by F2 plus 25. So your loss is 35, right? So in first case it is 35 at a frequency of 45 hertz. So 45 plus 25, yeah. So it was for 35 at 45 hertz, right? Yes. So 35 at 45 and F2 is asked at 55, right? 35 PC2, so that is your 70, this is your 80, so PC2 is 35 into 80 by 70, so PC2 is 40. So that was your question 5. Next question. A 132 kV 50 hertz three-phase transmission line with 2.4 cm diameter conductors is built so that corona takes place if the line voltage exceeds 230 kV RMS, if the value of potential gradient at STP at which ionization occurs can be taken as 30 kV peak per cm. Find the spacing in meter between the conductors, and here your surface regularity factor, basically MV, is given as 0.98, or just simply M is given as 0.98, and your air density correction factor is given as, sorry, irregularity factor is 0.94, and this is your 0.98. So assume that conductors are placed in an equilateral triangle and line is transposed. So here okay, V naught is G naught delta M R ln D by R. So that is already given as 232 kV RMS here, right? This is your V naught. So V naught is 230 by root 3 kV. G naught is, we know it is 30 kV. This is peak. Cm. Delta is 0.98. M naught is 0.94. Right? Yes. And R is 1.2. So from here to 30 by root 3, so G naught will be 21.21, right? This is in peak, so which is 21.1 kV RMS per cm into 0.98 into 0.94 into 1.2 into ln D by 1.2. So solving this, your D will be somewhat around 345 cm or 3.45 meters. Now coming to question 7. So three phase 220 kV 50 hertz 100 km long transmission line consists of 20 mm dia conductors spaced at 3.5 meter at corners of an equilateral triangle. Calculate critical disruptive voltage kVRMS between lines where T is 24 degrees centigrade, pressure is 740 mm, and surface irregularity factor M is 0.95, and your dielectric strength that you know, right? G naught at STP is 21.1 kV RMS per cm. Okay. So here we need to calculate the air density correction factor, which is 3.92 times P 273 plus T. So it was 740 mm. So in cm it is 74, and temperature was 24, right? 74 and yeah, 24 and 74. So this will come out as 0.9767. So your V naught can be calculated as G naught delta M R ln D by R kV RMS. So G naught is 21.1, delta is 0.9767, your irregularity factor is 0.95, R is how much? R is just 20 mm dia, so 10. So R is 10 mm or 1 cm. 1 ln and 3.5 meters. So 350 centimeters by 1 kVRMS. So this will come out nearly as 114.7 kVRMS. So V naught line to line will be root 3 times V naught. So that will come out as 198.6 kVRMS. Okay, now next question. Question number 8. So 8 is the same question, no, bit different. Similarly, 3 phase 220 kV, 50 hertz, 150 kilometer, OH transmission line, diameter 1.6 cm, spaced at 3 meter of equilateral triangle. So calculate your visual critical disruptive voltage kVRMS. Your temperature is 22 degrees centigrade. Pressure is 735 mm and MV is 0.92. Okay, so here we need to calculate the visual critical disruptive voltage. So similarly, first we calculate delta. So it is 3.92 times your B, which is in cm, so 73.5 cm, and 273 plus 22. So this comes out same as above, 0.9767. So your VV visual will be 21.1, or that is your at G naught delta MV R 1 plus D by root delta R ln of D by R kV RMS. So G naught is 21.1, delta is 0.9767, and V is 0.92, R is 0.8 cm, 1 plus D is 3 meter or 300, sorry, I have to convert it into cm. Sorry, this was I think a visual. Yeah, it was 0.3 R delta by ln D by R. Okay, so this is 0.3. So 0.3, 0.9767 into 0.8 cm ln d 3 meters, so 300 centimeters by zero point 0.8. So this comes out as 120.4 kV RMS. So this is phase to neutral. If you need line to line, so root 3 into 120.4, which is root 3 into 120.4, which is 208.53 kV RMS. Now next question. Using Peake's formula, determine total corona loss. Determine total corona loss in kilowatt in a rough weather condition for a 132 kV, 50 Hz, 3-phase, 175 km long transmission line, which consists of three 1.6 cm diameter stranded copper conductors arranged in a 3.5-meter delta. Assume temperature as 26 degrees centigrade, pressure as 750 mmHg, surface irregularity factor as 8.6, and of course G naught as 21.1 kV RMS per cm. Also assume that the disruptive critical voltage, basically foul weather condition, we saw that it was 0.8 times the fair weather condition, right? So that is only being said that the critical disruptive voltage under rough weather condition is 0.8 times the disruptive critical voltage under fair weather conditions. So let us see this. Okay, so here by Peake's formula, So P was 3 times of length of line L into 244 by delta into F plus 25 into R by D into Vp minus V naught square into 10 to the power minus 5 kilowatt. So this is under fair weather condition, so V naught dash. So let us first calculate V naught here under fair weather condition. So okay, so V naught under fair weather condition is G naught delta M R ln d by R. First we need to calculate delta. So it is 3.92 times it was 75 and 26. So that comes out as 0.9833. So V naught is 21.1 into 0.9833. M is 0.86, 0.86, and R is 1.6. So 0.8, 0.8, ln D is 350 by 0.8 kV RMS. So this will come out as 86.80 kV RMS. So this is fair. So V naught dash under rough or foul, that is 0.8 times V naught fair. So 0.8 times 86.80. So this comes out nearly as 69.44 kV RMS. So now using this formula, P is 3 into 175 kilometer. 3 into 175 into 244. Delta is 0.9833. F is 50 into your R is 0.8. D is 350 into operating at 132 kV minus V naught dash, which is your 69.44 square into 10 to the power minus 5 kilowatt. So this comes out nearly as 214.1 kilowatt. Now last question. So now it is using Peterson's formula. So calculate total corona loss for 3-phase 220 kV 50 hertz 160 kilometer transmission line having D equivalent equal to 625 R, and corona loss function capital F, it is given as 0.08. So here from Peterson's formula, the P is 3 into length of line into G naught into F into Vp square divided by log 10 D by R into loss function 10 to the power minus 5 kilowatt. So this is 3 into 160, 21.1 into 50 into 220 by root 3 square divided by log of, so it is D is 625 R by R into 0.08 into 10 to the power minus 5 kilowatt. So just let me check Peterson's formula. Yeah, so this was 2.1 F. Okay. So here basically 2.1. So this comes out as 83.2 kilowatt. So I hope these are all clear to you, this week's assignment. So this was mostly based on corona calculations for basically corona loss and the calculation of critical disruptive voltage. So I think then we'll meet next week and we'll close the discussion for this week now.